continue to offer this lecture in hybrid format with both a virtual and a live audience. Our speaker will present for approximately 45 minutes. We leave about 15 minutes at the end for question and answers. And for our virtual audience, throughout the presentation, please using the Q&A feature at the bottom of your screen, not the chat. And if you're using chat, good luck to submit your questions. And we will try to answer as many questions as possible during the question and answer sessions at the end. For our live audience, you can have chance to ask a question during the question and answer session as well directly. So we'll figure out. We don't have a microphone now in this room, right? So we just repeat the question. We're going to repeat the question. So Matt actually have a bigger job to do. So today is really wonderful to have welcome Professor Matthew Tresch from Northwestern University. And Matthew had the same condolences since September 2021, become the chair of the Biomedical Engineering Department at Northwestern. Congratulations, condolences, and he has done a fantastic job. And he's a professor of biomedical engineering, physical medicine, and rehabilitations and neuroscience at Northwestern University, and a principal investigator at the Shirley Ryan Ability Lab. He received his bachelor in psychology at Wesleyan University and his Ph.D. in neuroscience from MIT in the laboratory of Amilo Bizzi. After his doctoral work, he was a postdoc fellows in Ole Kohn at the University Copenhagen. That's wonderful, doing a overseas postdocs, and then returned to MIT shortly as a research scientist, then studying at faculty at Northwestern. And please give us a warm welcome to Professor Tresch.
Okay. Thanks for the introduction, Ed. I really appreciate it. And thanks for having me out for the visit. It's been great so far. I will go ahead and project. I'll share screen. This one or down? There, yeah. Okay. What's this? We good? Or... Okay. Okay. So I appreciate the invitation. It's been great to talk with people so far, and really appreciate just seeing Columbia BME. Really fantastic. Okay. So I think what I've kind of learned from being chair is kind of obligated, part of my contractual duties is to talk just briefly about Northwestern BME. So I have to kind of just put that in here. Let's see. Keyboard is not, there we go. So like you all, I think we have a lot of similarities to Columbia. We're kind of split across two different campuses, right? So we have our engineering campus up in Evanston. So we have this kind of nice, beautiful liberal arts college up in Evanston. Lots of humanities and cultural things going on here. But then downtown, you can see here, that's where our medical school actually is as well. So my lab is actually downtown in the medical school, but when I'm putting on my chair hat, I actually am up here in the engineering school as well. And this, like you all, it's a challenge, right? There's two different campuses, but it's also really exciting because like you all, we are very much embedded across the university, right? So this is just a really nice kind of, network kind of connection diagram where here's a BME's department. And then each of these different nodes is an interaction with another unit across the university, right? So clearly we have lots of interactions with the medical school, like a huge kind of footprint there. And that's because our faculty are embedded in the medical school, as well as having co-appointments and having lots of collaborations, but also lots of collaborations with other engineers. These are the other purple nodes here, as well as kind of in the liberal arts college as well. So one of, like you all, BME is a really exciting place to be because we kind of have our, I kind of think of us as a metastasis of this, that's my negative sense, but we're kind of embedded in all over the university and gives us, like you all, access to lots of really exciting research and opportunities. So it's really fun. The other really exciting thing that just kind of happened here is we had the announcement, really exciting in Chicago, to having this announcement of the Chan Zuckerberg Biohub in Chicago. This is the second biohub they've kind of invested, and it's a way to kind of create this really great infrastructure for doing biomedical engineering research. And this is collaboration across the University of Chicago, Northwestern, UIUC. So we're really excited by this. It was just announced last week. There's going to be space downtown for doing this kind of research. Our leadership is coming from people like Shana Kelly at Northwestern, Jeff Hubble at University of Chicago, and Rashid Bashir at UIUC. So we're really looking forward to kind of seeing where this goes and just kind of the seeding of the way this is going to kind of precipitate the research of biomedical research here in Chicago, or there in Chicago. So anyway, that's my obligatory spiel for Northwestern. I think lots of really fun things going on. And it's been really fun as a place to be chair, just because everybody, like here at Columbia, everybody's very collegial, everybody's very ambitious, it's a really positive community to have in time. So what I'm going to talk about is my own work here now. So that was the exciting things, everybody else work. Now you get the boring, kind of more mundane talk about my own research here. So the work that we do in our lab looks at the neural control of movement, right? So how does the nervous system produce the movements we do every day? And we come at this from a basic question side of how does the nervous system actually accomplish this, right? To me, that's just amazing, right? All the things we do every day, these kind of hand gestures I'm making, I'm balancing, doing this all without any kind of conscious awareness of it, right? And it's just completely automatic. How does that happen, right? What are the neural processes involved with that? What are the sensory processes that are monitoring our execution of tasks, et cetera? How is that actually done? And to do this, like, anything in neuroscience requires this integrative approach, right? We need to be studying animals' behavior. We need to understand the nature of the problem, so the mechanics of the limb as well as the environment. And then how does the neurophysiology, the neural systems, how do they interact with the environment to accomplish those behaviors, right? So we try to take all of these different approaches so that we can gain insights into all these different levels as we go, okay? And then we try to take that basic information and then leverage it for things like rehabilitation, right? So how do we take our knowledge of how the nervous system produces walking normally, and then use that to leverage it to understand how it can be leveraged after spinal cord injury or stroke or other ways of doing things, right? So that's our general approach. So like I say, our basic question is kind of, in some ways, can be, I don't know if I can put that off to the side. In the context of motor control, one of the basic questions that people ask is, how does the nervous system decide which muscles to choose to produce a movement, right? We kind of take this for granted in a lot of ways, but it's really actually a complicated problem. But the way we usually think about this is kind of, how does the nervous system activate our sets of muscles or individual motor units and populations of motor units in order to achieve task performance, right? So here's just a simple case. We're trying to produce a knee extension. You can think of this for walking or kicking a soccer ball, something along these lines. And we specify the problem in terms of the task, right? So how do we produce the correct kinematics of the limb to kick the soccer ball? How do we use our correct joint torques to give the correct force that will produce the goal scoring kick and so forth, right? So all of these things are phrased in terms of we need to achieve that final task outcome. And then we look back to the muscles and say, okay, how do the muscles actually influence task accomplishment, right? So how do we think about this, here's 3 muscles activations. How does this muscle, and this muscle, how do they make their contributions to produce the correct joint torques and kinematics in order to achieve task performance? Then we throw in some sort of optimizations, figure out what's the correct muscle activations to achieve that task. Okay, so that's kind of our standard approach. And that was very much my own approach, kind of, when I was starting my lab, it's kind of like, we need to understand these questions. However, what have I done? Oh, I see it, because every time we activate a muscle, in order for the muscle to interact with the environment, it has to act through our joints, right? So in the case of these kind of knee extensions, in order for a muscle, our quadriceps muscle, to produce that kind of extension of our knee joint, it has to act through the knee, right? And this was amazing. I sat down with Yassine Dar, who works on knee biomechanics in humans. And we did a section of the rat knee joint together, and keep on looking and doing dissections, like, where's the joint? Where is it? It's not there. We think about from robotics that a joint should be this kind of revolute pin joint that has like a pin going through and then it kind of rotates around. The knee joint is just a phenomenon, right? It's these 2 bones next to each other, connected by ligaments and tendons and so forth, and cartilage. And they just are designed in such a way that they permit movement in certain degrees of freedom and constrain it in others, right? So it has no resemblance to what we think about in terms of robotics along these lines. And of course, in order to produce this kind of simple just knee extension, we can activate muscles in different ways that will cause different stresses and strains within the joints, right? So we can have lots of different ways we can activate our muscles, which can all produce the same knee extension, that all can have a goal-scoring kick, right? But they will come at different internal stresses and strains within the joints, right? And this has real consequences, right? Yes, I can, at any given time, I will win the soccer match, and well, I won't, but somebody might, get the correct kick and achieve task performance. But if I kept on doing this in a way that produces aberrant stresses or strains within the joints, it can have real consequences. We can have a dislocation of our joint. We can have a rupture of a ligament. We can have osteoarthritis, right? And so all of these variables, though, are kind of hidden, right? We don't see them when we're actually kind of walking down the street or kicking a soccer ball. They're all kind of buried behind the scenes, and they're not manifest in task performance. And so we just wanted to ask is kind of, how does the nervous system care about these joint variables, right? And kind of, can we define a paradigm to show how it might regulate this? And will this give us insights in terms of neural control of movement and the strategies the nervous system uses to specify muscle activations to produce a behavior, okay? So what we're going to do then is, and this has real consequences, I guess is the point, right? It's obviously in terms of joint injury and so forth, but also for rehabilitation, right? So when we think about doing rehabilitation after an injury, right, after spinal cord injury or after a stroke, a lot of times the therapist's goal is to get the person back to what they were doing before the injury, right? And you've achieved success when you look at that person and they walk like they did before, or they do their tasks like they did before. And then you're like, they're back to normal. That's great. However, if you think about somebody who has an injury, so let's say you have something like, an ACL rupture, right, where the mechanics of your knee joint have changed, right? In that case now, the transmission of forces across your knee joint might have changed. And so the stresses and strains that were produced during normal kinematics of walking might now be very aberrant, right? And so the best thing to do after an ACL rupture might not be producing those same patterns of kinematics that you did before, because it might come at the cost of those aberrant stresses and strains within the joints, right? And that's actually, after ACL rupture, there's something, 70% incidence of osteoarthritis after reconstructive surgery. It's a, major issue afterwards, right? And the same thing after stroke, right? If your neural control ability has changed in different ways after an injury, maybe you shouldn't be trying to retrain those kinematics that you had before, because in order to achieve that, you need to produce aberrant stresses and strains in the joints and things. So maybe what actually is better to do is that you should figure out, after an injury, how do you accommodate task performance, but also need these internal stresses and strains in order to kind of optimize these two sets of variables? Okay, so what we wanted to do is look at this question and kind of have an animal model to look at it tractably in a series of controlled experiments. And we work with rats, and we kind of constrained our problem to look at control of quadriceps muscles and forces within the patellofemoral joint, okay? So just some basic anatomy. You all have your quadriceps muscles. Hopefully you're somewhat familiar with them. There's 4 of them, hence the name. We've got vastus medialis. This is the one that's sitting inside on the medial surface of the leg. Vastus lateralis on the lateral side. Rectus femoris, which goes along the middle. And then buried underneath, which is close to the femur, is vastus intermedius. Okay, these are the 4 muscles. They all insert onto the patella. Okay, and then the patella, through the patellar tendon, attaches to the tibia to produce the tibial force. Okay. And so we were doing these experiments. This is actually our gateway into these experiments. We were trying to build a musculoskeletal model for the rat hind limb. And we were trying to do this by simulating individual muscles, characterize what they do, and then put that into our model. And we did this, so we went in and stimulated individual muscles. We stimulated VM and VL, okay, and did this separately. And then we measured the forces and moments across the skeleton, okay, and measured at the ankle. So we attached a force transducer to the skeleton, fixed the limb at one position, and then measured the forces, 6 degree of freedom forces and moments across this, right? So black traces are VL, red traces are VM. And then each of these different arrows is when we put the limb at a different point in the workspace, okay? And what you can see is that the direction of the forces, and this was true here just in the plane, but across all 6 degrees of freedom for these 2 muscles was indistinguishable, okay? So these muscles in the rat are completely redundant, right? We could swap out one or the other, activate, we could double the activation of VM, half the activation of VL. We would have the same endpoint interaction with the environment, the same contribution to task performance, right? So complete redundancy in terms of task performance, okay? However, as you might expect, what we did is then if we put our force transducer on the patella, lifted it out of the groove, okay, and measured the forces there, both of these muscles are pulling proximally towards the hip, right? Because they're, that's how they're pulling on the patella, but they have a differential medial lateral force, okay? So VM is pulling medially on the patella, VL is pulling laterally on the patella, okay? Because the patella sits in the patellofemoral groove, these medial lateral forces are not transmitted to the tibia, okay, but they're kind of accommodated for interaction forces on the patella instead. So the patellofemoral groove is acting as a mechanical filter, right, along these waves. But the idea then is that we have now two different ways of characterizing the contributions, the actions of quadriceps muscle. In terms of task performance, VM and VL are entirely interchangeable. We can swap one for the other, right? They're agonists, right? In terms of their consequences, in terms of internal joint actions, however, they're antagonists, right? One is pulling medially, one is pulling laterally, right? And so now these muscles, we have kind of a framework to think about. We can push these, put these different actions of these muscles against one another and start beginning to ask, how are these muscles controlled or activated to control either task performance or these internal joint variables, okay? So we're going to design some experiments to go after these questions as we go forward. Just to round out the picture, here's the actions for the other quadriceps muscles. So rectus femoris is actually biarticular. So it has a knee extension moment like the vasti muscles, but it attaches at the hips. It also has a hip flexor moment. Okay, so from a task performance point of view, RF does something distinct from VM and VL. Okay, VI is another vastus. It's also monoarticular. It has a pure knee extension torque, right? So it is also completely redundant with VM and VL. In the context of these internal joint variables, however, VM and VL, again, are antagonistic, pulling mediolaterally, but RF and VI, because they're kind of along the midline of the femur, they don't have a mediolateral force, a significant mediolateral force on the patella. Okay, so they're neutral with respect to this internal joint variable. Okay, so this is kind of the biomechanics that I like, right? We don't have to invoke a really complicated biomechanical model using finite elements and so forth, right? We have a kind of a conceptual model where we can make very clear predictions. So, we kind of know how these muscles act, in either task performance or these internal joint variables. And so we can design some experiments to ask, how are these two different sets of variables controlled by the nervous system across different conditions? And we're going to do this to ask this question, does the nervous system actively control quadriceps muscles to minimize the net medial lateral patellar forces during behaviors, right? Does it care about the set of internal joint variables? Okay, so we're going to do 3 sets of experiments to show this. Okay, so the first set of experiments is just looking during normal locomotion. And we're going to look at the correlations between quadriceps muscles just during repetitions of walking. So the idea here is to say that if the nervous system really cares about simplifying task performance, well, VM, VL, VI, they all do the same thing for task performance. They all give us this knee extension torque. So it would kind of make sense, maybe they should be controlled as a single unit, right? This is kind of invoking ideas of muscle synergies or kind of functional modules, things along these lines, right? So if that's the case, then the correlation between VM and VL should be the same as the correlation between VM and VI and VI and VL, right? All of these muscles do the same thing. So they should all have the same correlation strength between them all, right? So that's if the nervous system was trying to simplify task performance. If, however, the nervous system is trying to regulate joint stresses and strains within the joint, then what we should see is that there should be a very high correlation between VM and VL instead, right? Because basically every time VM goes up, that's going to produce a medial force on the patella. We should want to increase activation of VL as well to kind of counteract that so that the net force on the patella is balanced and we minimize that, right? Whereas, and then these two muscles should be correlated together, but the correlation of these muscles to VI, we don't care, right? Because that has no impact on the net mediolateral force on the patella, okay? So that gives us kind of 2 different sets of predictions in terms of how these muscles should be coordinated during behaviors. So we just do this. We record from EMGs chronically in these animals for days and weeks as animals are just walking, right? So this is just an example. Here's the 4 quadriceps muscles. This is iliopsoas, just a hip flexor muscle to show you kind of stance versus swing back and forth, right? And so we can collect many hundreds of these steps and look at the kind of the trial to trial correlations of these muscles across repetitions. So this is just showing you kind of across different task conditions. Each one of these traces is the average activation of one of our quadriceps muscles. So VL is in blue, right? And this is the step cycle. So this is stance when the foot's on the ground. And then when this is the swing phase, when the animal's, inflection across this. And this is the activation of our quadriceps muscles across the step cycle for each of the 4 quadriceps muscles. This is now varying, the top trace is varying the slope of the treadmill, right? So it's either level, it's down slope, or it's up slope. This is varying the speed of the treadmill at level, okay? And what you can see first off is the quadriceps muscles, they change the profile across task conditions. So if you take, let's say you take VL in blue, you can see as you go from down slope to up slope, to level to up slope, you get this increasing activation of these muscles. So that makes sense, right? You're changing task requirements, you change activations of the muscles. What you can see, however, is that VL and VM change their task performance in the same way, right? So VM and VL are doing here, they're on top of each other when they're down slope. They change when you go to level, but they change in the same way, and they change in the same way when you go to upslope as well. And that's also true across speeds. Other quadriceps muscles are changing across the task conditions, but they're changing in a way that's different, right? So whether you look at VI in green or RF in black, they're changing, but they're not changing in the same way as VL and VL. So this is consistent with the idea the nervous system is tightly correlating these 2 muscles so that you minimize net patellar forces. This is across different task conditions, right? You can also look at it, yeah. Sure.
For the different speed here, what's the condition level or the task?
So,
The
yeah.
bottom part here, the level, you're just working on the flat surface with different speed.
Yeah. So the question's asking in the bottom trace, what was the slope of the treadmill? These are all taken at level cases, exactly. So roughly speaking, there are slightly different trials between these 2, right? Because we had like more data here is slightly across, but roughly speaking, you can see they have very similar profiles across these 2 conditions. Another question? Sorry, yeah. So the question is, what is the x-axis? So this is the percent of the step cycle. So the idea is we're kind of defining, from toe down, which would be at 0. Okay, and then this black trace is the foot is on the surface, the entire stance phase. And then at this point from the black trace, then we have foot off. Okay, and then at 100%, that's the end of the step, and then you go back to hitting the contact again. Okay, so basically, you often define locomotion as kind of a circular variable, right? Because it has this kind of recurrent pattern to it that way. Yeah.
So just to have a picture of what this looks like, you have implanted electrodes, like several of them in different levels, and it's like remotely, this data is remotely sent to your data acquisition system, or are there a bunch of wires and just to get sort of a picture of what it looks like?
Yeah, so these experiments are all, so you're right, we put in pairs of bipolar electrodes and about 15 muscles in the hind limb, and then these ones are tunneled to a connector on the back. Okay, and then that's tethered to the acquisition system as the animals are walking. We've done some wireless work as well. It's just for these experiments, so it's constrained enough that it's fine. And these will stay viable for, we've done it up to like 8 months with stable recordings afterwards along these lines. Great, cool. Yeah, thank you for the questions, and please chime in as they come, definitely. So that was across task conditions. We can do the same thing on repetitions of steps, right? So from one step to the next, how are these muscles correlated, right? So this is now looking, each one of these dots is the activation of VL and VM on one step, right? So VL, this dot is on, VL was activated high on this step. VM was activated about average on that step. This dot, another dot is a different step and so forth, right? So this is looking at the trial to trial, the step-to-step variation, covariation of these muscles. And what you can see is that VL and VM are fairly tightly correlated with each other. The other pairs of quadriceps muscles also have a correlation, but it's not as tight, okay? So VL and VM are very tightly correlated from one step to the next. When VL is activated a little bit more, VM also tends to be activated a little bit more. And we saw this robustly across different task conditions and across animals. So this is now looking at different slopes, okay? Again, different speeds. This is the correlation coefficient between pairs of muscles. This first one is the correlation between VM and VL, and which you can see is across all these conditions, it's high, okay? And moreover, if we look at the correlation between all the other pairs of muscles within the quadriceps, they're not zero, but they're not as high as VM and VL, okay? And importantly, the correlation between VM and VI and VL and VI is lower than the correlation between VM and VL, right? Again, all of these vasti muscles have the same contribution to task performance, right? So if it was task performance, we would say they should be all tightly correlated. Instead, we're seeing a preferential correlation between VM and VL, consistent with the idea that the nervous system is monitoring and minimizing this net medial lateral force on the patella. Okay? So this is kind of consistent with the idea the nervous system cares about these variables, right? So that's one experiment. And of course, it's just observation, right? So what we wanted to do as well is do some perturbation experiments to go after this in addition. So a very obvious thing that we could do is attach a load onto the patella and look at adaptation, right? So the idea is if we put on a load, that pulls laterally onto the patella, then the prediction is that the nervous system should change the balance of activation between VM and VL so that it will minimize that net force on the patella. In this particular case, if we put a lateral load on the patella, we should increase activation of VM or decrease activation of VL to accommodate that, right? So that's what we tried to do. And these are kind of heroic experiments. They're really difficult to do in a rat, but you can do them. So we can put a bone screw into the patella of the rat. It's small, but it's there, okay? We can put a bone screw into the lateral face of the femur, okay? So the sequence is that we insert those screws, we implant the EMGs, okay? Then we let the animal recover and get our baseline EMGs. So this is kind of our no perturbation condition. What we can then do is do a brief surgery and just put on a rubber band between these two screws, right? So we don't have to deal with anything to do with the implantation. We've dissociated the implantation surgery from the putting on the rubber bands, right? So we attach that spring, and then we measure the ratio between VL and VM over a 1 to 2 week period of time. And then what's kind of nice about this one is we can go in and then we can cut the rubber band and look at de-adaptation as well, right? And see how the ratio changes, okay? So that's what we did here is kind of just an example. This is now our 3 conditions. So this is VL and VM on 3 steps, okay, when the no spring is attached. Bone screws are implanted here, right? So that's in there. And we have some particular balance of activation between these muscles. We now attach the spring. This is going to pull laterally on the patella. And what you can see is we see a decrease in the activation of VL, okay? VM activation is about the same, okay? We now go ahead and cut the spring, and VL activation goes up again. In this animal, we saw a small increase of VM as well, but the ratio between VL and VM is much, there's a higher ratio here than, and it's similar to what there was with no spring than when the spring was attached, okay? And that is true across animals. So this is the ratio between VL and VM, normalized to the no spring attached condition, okay? And you can see when we attach the spring, the ratio goes down, meaning that there's a net medial force on the increase of the medial force on the patella, or a decrease of the lateral force, as you think about it. And then we cut the spring and it goes back to similar levels than it was before, okay? So the nervous system is changing the balance of activation between these muscles to accommodate for this medial lateral force on the patella, okay? Yeah, question.
What is the typical time period between each of these 3?
So we're doing this like about 2 weeks, okay? It's kind of so these are taken in the 2nd week after either the spring attachment or the spring detachment here as well. There's some interesting things to come back to about more of the short-term question there. So, okay. So again, consistent with the idea the nervous system cares about this. So the 3rd experiment is kind of where I think it's interesting, or we do another experiment with perturbations. And I think this is kind of nice because it really, the adaptation process afterwards really only makes sense if you start thinking about joint variables in a lot of ways. Okay, so anyway, kind of walk through this kind of the logic here. So if you think about quadriceps control in your baseline condition, right? You've got some activation of VM, RF, and VL. I'm just kind of ignoring VI for now for simplicity. We can bring it back later. And those are producing some muscle forces, which are going on the pulling on the patella, which give us some net aggregate joint torques, right? So some combination of knee extension and hip flexion, the hip flexion coming from rectus femoris here, and some combination of medial lateral forces on the patella, right? And so the idea is that these are achieving the task performance. These are balancing the medial lateral forces on the patella. So now let's go in and do a perturbation. And the perturbation we're going to do is paralyze one muscle. So we're going to go in and paralyze VL, okay? So this has consequences both to task performance, right? You're going to lose that knee extension torque that was there before. So you're not going to produce the task as you did before. And you're also going to lose this lateral force on the patella as well, okay? So you're getting perturbations for both of these sets of variables. So what we can ask is how should the system adapt, right? So if the nervous system really cared about task restoration, then what the easiest thing for it to do is just increase activation of VM, right? VM and VL do exactly the same thing as far as task performance goes. So all the nervous system has to do is just increase activation of vastus medialis. Boom, you're done. You got the same pattern of joint torques and the animal walks as before. Obviously, however, this comes at a big cost in terms of these internal joint variables. You're going to have a very aberrant, a very large net medial force on the patella. So that will be bad in terms of those sets of variables. Conversely, if you really cared about medial lateral force and these internal joint variables, what you would want to do then after paralyzing VL is shut down VM, right? So that you end up with no medial lateral forces on the patella. That's great from that point of view. And then preferentially increase rectus femoris, right? Because that's going to pull straight along the patella. You'll get your knee extension torque that you wanted before. However, this will complicate things in terms of task performance because now you're going to have that kind of aberrant hip torque that rectus femoris produces as well. So from the point of view of task performance, just increasing rectus femoris is going to come at a cost. It's going to make your task performance come at a cost, or so if you just increase rectus femoris, it's going to compromise task performance and come at that cost there, okay? If instead the nervous system kind of cares about both of them, maybe it's going to find a compromise. It will maybe increase activation of rectus femoris, but maybe maintain activation of vastus medialis so that it has, okay, some medial force on the patella, but maybe it's not enough to really kind of cause damage, and some aberrant hip flexion torque, but maybe enough that it can kind of accommodate, okay? But the idea here is that we can kind of make these predictions about interpreting the pattern of adaptation across these muscles and interpret what is the nervous system actually trying to control when we see these different adaptation strategies, okay? So that's what we're going to go in. We go in and we cut the nerve to VL, right? That paralyzes the muscle. So this is activation of VL across 3 steps here, okay? We can shut down the muscle. There's maybe a little bit of residual kind of motion artifact or crosstalk. Can never get rid of that entirely. But basically, this is the activation before, average across the step cycle, and it basically shuts these down for 1 week, and we don't see regeneration after 2 months of 7 weeks of this process, okay? So we've shut down VL. This is showing kind of an example of the adaptation process. So this is rectus femoris and VM before we cut the muscle. So rectus femoris has this characteristic biphasic activation where it's active both during the swing phase with this burst here, as well as during the stance. But what you can see, so there's some activation of VM and RF during the stance phase. 1 week after the paralysis of VL, we see an increase of activation of both of these muscles, right? So RF goes up quite a lot, but so does VM as well, okay? But by the time we get to week 7, what we see is RF activation is maintaining its increased activation. VM activation is it's maybe a little bit increased, but more or less what it was before. And that's just kind of shown in these averages here. So the blue trace is rectus femoris before the cut, okay? It goes up quite a lot initially, but by this gold, this is week 7 after the adaptation, it maintains its increased activation, okay? VM instead, okay, it's maybe a little bit of an increased activation that's maintained, but it's not nearly as much as the increase of rectus femoris, right? So there's a preferential increased activation of rectus femoris after VL paralysis, right? And that's just kind of holding up here. So this is looking at RF activation across our animals. And if you look at compared to baseline, RF is increased its activation after 7 weeks, okay, and that's maintained, right? But VM across our animals goes back to indistinguishable from baseline. Okay, so there's a preferential, after VL paralysis, animals preferentially increase rectus femoris in order to restore that paralysis, to accommodate for that. We also see that this is not just in terms of neural activation, but we actually get changes in terms of muscle mass. So, with increased activation of the muscle, you expect the muscle to get hypertrophy as well, and that's what we see. So the mass of rectus femoris goes up after 7 weeks, whereas the activation of the mass of these other quadriceps muscles doesn't change. Okay, so it's both neural adaptation as well as muscular adaptation that we're looking at. Okay, but what it's saying is that what this is suggesting is that the nervous system is out here, right? It's kind of compromising task performance and joint control. So the fact that it increased rectus femoris only really makes sense if the nervous system cared about these medial lateral forces, right? If it only cared about task performance, we'd see VM go up entirely, right? So, but notably, it does not get rid of the activation of VM, right? VM doesn't go to zero, right? It still maintains some activation of VM there as well. So the idea is it's finding this compromise between these two sets of variables. But again, like I think what's, for me, what was interesting is people have done a lot of these kinds of experiments where they've gone on and do perturbations, paralyzing a muscle, deafferenting something along these lines. And they show, yes, the nervous system changes the activations of muscles. But in this case, we saw that, if you ignore these kind of joint stresses and strains, you wouldn't be able to make much sense of why did the nervous system increase rectus femoris. It really, there's no, from a task performance, it just makes things harder, right? So you really, by paying attention to these extra variables, you gain insights in terms of neural control strategies that otherwise might not be apparent. Okay. So just kind of interim summary conclusions. I think, just kind of showing you 3 sets of experiments, which I think, for me, I think, none of them are necessarily definitive, but taken together, I think provide good evidence that the nervous system cares about these internal joint variables when they're choosing how to activate muscles along these lines. So obviously, this is kind of just a starting point. What we want to do now is use this to kind of go into neural control. And for me, this is where it gets really kind of exciting. I've always, I'm very interested in kind of spinal circuitry. That's been my background entirely. And oftentimes we look at spinal circuitry in the context of locomotion, okay, which is fantastic, beautiful work. I'm not smart enough to understand kind of the control problems involved in locomotion well enough to make predictions in terms of neural control and neural circuits, right? Understanding what kind of sensory information should be coming into the spinal cord, to which muscles and so forth, how should that be distributed? That's quite challenging to understand that from a kind of an optimal control or, a problem-based kind of strategy. Whereas these kinds of questions about joint control, I think, we have now, they're more tractable. We have very clear predictions in terms of, if we have a neuron in the spinal cord that's involved in this, what sensory information should it be getting? And if it gets that sensory information, how should that outflow in terms of influencing muscle activation patterns and so forth? Question? Sorry.
Yeah. So, why would, I understand kind of why you expect the end to take against whenever you balance the other you study the end to take against the concept of work. But if like for me at least, I was thinking that why would you expect that if you need an opposing force to the end? So I would have expected it to try to talk like the other as well.
Because of the joint torque? So,
yeah, exactly.
But in terms of the task performance, you're saying?
Exactly.
But so those are totally valid predictions. I guess the way that we were kind of thinking about it though is that if you spread it to RF, you're going to end up with these extra hip torques, which means you're not doing the task in the same way. And that you now need to ways to accommodate for those extra hip torques as well. Okay. And so the idea is that, yes, you can do that and do that sharing, but then you're no longer walking in the same way. And maybe it requires other muscles to counteract those kind of aberrant torques, or you're going to have kinematics that are going to look different and so forth. And we have a side analysis, a different story that kind of comes out from that I just don't have time to talk through, but could talk through more afterwards as well. Yeah, sure. So like I say, we're kind of heading forward, right? But these are kind of suggesting nervous system cares about these variables. We want to get to the next question is, how does it actually accomplish this control, right? And so the first question is just asking, how does the nervous system monitor these different, these joint variables, right? And so I'm just going to go through this relatively quickly, but there's a few different possibilities, right? And here we're kind of just asking, for this correlation we see between VM and VL from one step to the next, how is that accomplished, right? So one idea is that this could be done through joint afferent, joints, right? So there's lots of sensory information coming from the joints. It's always been a little bit mysterious of what these joint afferents are actually doing, right? But one idea is that they could be monitoring the medial lateral force on the patella and then having a feedback loop to the balance of activation between VM and VL to minimize these things. So that's one possibility. Another possibility is that muscle proprioceptors could be doing this, right? So we could be indirectly estimating the medial lateral load on the patella by monitoring the forces in the quadriceps muscles, and then just using kind of like some sort of internal model of how those forces in those muscles translate into forces on the patella, estimate those medial lateral forces, right? Another way to do this is you could do it entirely feed forward, right? You could just have spinal interneurons which project to VM and VL and give you that balanced activation. So every time VM goes up, they just obligatorily have to go up in VL as well along these lines. So we just wanted to get started with this by looking at joint afferents, okay? And as I say, the role of joint afferents is varied and complicated. And just suffice it to say, there's been lots of experiments on this and it still remains kind of murky, you know, of exactly what's going on. Some people have shown that there's actually huge deficits in terms of kinematics during walking. If you put in lidocaine into the knee joint, that can cause large problems. There's reflex changes that can happen from these afferents as well. So the idea is that they could be playing a role, but you know, it's currently unclear. So we just wanted to go in and ask, and so kind of the first starting point towards this is this time course question here, right? So if the joint afferents are being used to kind of monitor the load on the patella, right? Then what you would expect is as soon as we put the spring on the patella, we should see a change of the balance of activation of VM and VL, right? Because if it's kind of being used in this really rapid feedback loop, we should see that. We don't see that, right? So this is, again, the ratio between VL and VM. This is before we attach the spring. This is 3 to 5 days after attaching the spring. And we see that over 5 days, the ratio changes. But 2 hours after putting on the spring, we don't see a change of the ratio, okay? So this is suggesting that these afferents aren't being used, you know, necessarily in this rapid feedback loop, right? It's more of a slow adaptation process. So that's one point to get at that. But we wanted to go a little bit more directly. And so for these ones, we just did lidocaine experiments into the knee joint to anesthetize the knee joint reversibly and look at the effects on control and on coordination, right? And, you know, this is just recordings from the articular nerve to show that we can suppress it with lidocaine, okay? And that reverses. Each one of these is a tap of the knee joint showing a burst of activation in this nerve. So the first thing, well, I'm just going to jump to the control of the correlations, right? So what we wanted to ask is, when we put in this lidocaine into VL and VM, does it change the correlation structure between quadriceps muscles, okay? And in particular, does it change the balance of activation, the correlation between VL and VM? So the black trace is before lidocaine, the red bars are after lidocaine, and what you can see is the correlation strength between VL and VM before and after doesn't change, okay? So lidocaine shutting down these joint afferents doesn't change the balance of correlation between these two muscles at all. Interestingly, the correlation structure between VM and VI and between VL and VI, the other vast eye muscles here, did decrease after lidocaine, okay? So on the one hand, you know, this was really nice because it gives us a nice positive control. You know, our lidocaine is doing something and changing things, which is always reassuring to have that. And it does suggest that these joint afferents are doing something in terms of the correlation structure between quadriceps muscles, but maybe not the correlation that drives the patellar femoral loading condition in these ways. And this is just a sham control showing that, you know, these changes were not they were reflecting the lidocaine per se. I think I'm just going to skip over these. Just suffice to say, we looked at it in the adaptation process as well and didn't see any effect of lidocaine in the adaptation process either, okay? So it seems like, you know, the moment-to-moment correlations didn't seem to change anything, and it didn't seem to change after we paralyzed VL along these lines. Okay. So it looks like what you conclude is, at least for our initial observations, joint afferents don't seem to be important for normal behavior. I didn't show you that, but they didn't change kinematics. They didn't change the average activation of our muscles across the step cycle. We didn't see joint afferents. They were not important for correlation between VM and VL, right? So that kind of cycle to cycle correlation didn't seem to be important. And they don't seem to be driving reflex EMGs after VL paralysis, after these aberrant, the change of loads after VL paralysis, okay? Caveat, they could be involved in driving these long-term adaptations. All of our experiments that we've done with lidocaine are, you know, are temporary suppression of the afferents. We haven't done any long-term suppression of the afferents to see if it changes that long-term adaptation process. So that still is a possibility. Okay. So what we want to do then is kind of continue those experiments with joint afferents, but then also look into muscle proprioceptors as well. So these are, I think going to be really a lot of fun. We've been talking to people. There's a collaborator we're working with now is Elie Zelzer at Weizmann Institute. He has mice that are knockouts of muscle proprioceptors, and he shows these mice end up with really kind of dramatic joint dysplasias. So the development of their joints is very aberrant when you get rid of the proprioceptor muscles, proprioceptor afferents, suggesting that these proprioceptors are important in regulating these joint stresses and strains during development. And so we want to kind of use the same approaches to ask, we see similar deficits in the adults if we can do these kind of transient silencing these afferents in adults. But then also we want to look at whether there are spinal interneurons that are involved in this control. So just simple ways are the last order interneurons that project to both motor pools in VM and VL. Okay. So anyway, the idea is that, what I hopefully kind of suggested is that the nervous system does care about these variables, which I think expands the way we think, or expands the way I think about motor control. Right, from the point of task performance, those are important questions. But there's this whole other set of variables that are kind of hidden that we don't usually think about, but the nervous system really does care about in terms of specifying muscle activation patterns. And so a lot of the kind of questions of motor control about, how do we control all the different muscles in our limb, maybe some of those questions become reframed if we think about not how do we achieve task performance, but how do we do it in such a way that doesn't cause joint damage at the same time. Okay, so these are kind of experiments as we go forward. So first off, just wanted to acknowledge the two postdocs who are really kind of critical in this, Cristiano Alessandro and Felipe Barroso. They've now gone on to faculty positions at Milan and in Madrid, but they really are the ones who did most of these experiments, along with other, Ben Rellinger was some kind of initial PhD student who started some of the experiments with the VL paralysis, and then some research techs as well who are critical. These are also, as I said, collaborations with Tom Sandercock and Yassine Dyer, who provided a lot of kind of the motivation for this work. Dinesh Pai and Chi Wei helps with some of the modeling that we've been doing as well. And these were funded by NIH and NSF for these experiments. So thanks very much.
Thanks very much, Professor Tresch. It's a fantastic talk. So if you can unshare, and then our background will set up different pictures. So before we get into questions, I would like to call everyone's attention to our next hybrid seminar, which will not take place next week. And because next week is our spring break. So for students here, enjoy your spring break. So next seminar will be 2 weeks away from today, and March 24th with David Unimus from Purdue Universities. And please follow us on social media for receive latest updates. You can see our social media information on the slides, and you can always access the registration information and our BME seminars on our website, and also now we have our speakers' contact information there as well. Let me turn to Professor Lisa Olson to answer the question, because it's much easier, because then
you can answer the question.
Yeah.
It's perfect. It's perfect.
She can control both the.
Okay.
You need a microphone.
So I think we'll take questions from the audience here. So far, none coming in from out in the bigger world. So any questions? We already had a few, but yep, you.
Repeat. Yeah.
In the very beginning of your initial experiments, when you said you were stimulating muscles, how do you actually do that?
Yeah. So the question is, when we're actually stimulating the muscles to measure their actions across the skeleton or the patella, how do we do those experiments? So there's two ways, basically, and they're just kind of really straightforward. We either can isolate the nerve to the muscles and then put it onto hook electrodes and then stimulate the muscle directly to cause kind of, complete tetanic activation of the muscles. That's great, because then we can get full activation of the muscle. Getting the nerve to the different quadriceps and getting the different branches can be a little bit tricky. A lot of these branches are quite small in the rats, and so getting good, isolation of them can be challenging, especially in situ, because what we're trying to do is measure it with the animal in vivo and intact conditions, so we can't kind of like lay it out and do things. So that can be challenging for these muscles in particular. So the other way to do it is we just put in intramuscular electrodes into the muscles and then stimulate directly in the implanted electrodes. It's not as good because we can't get full activation of the muscles. We're kind of constrained by the nerves that are near to our electrodes. And we have to watch out for spillover to adjacent muscles as well. But those are things we can usually control. And for these experiments, we didn't really need to activate the muscles maximally. We just need to know kind of what was their pulling direction and how they compare to one another. Good. Yeah. Okay. Yeah. Sure.
Yeah, great talk. For the second experiment, where you apply the load to the lateral load, just we play around with that in different forces. Did you experiment with like increasing the load?
Yeah, so the question was, do we play around when we did the patellar spring experiments, did we do anything to change the load that was applied to the patella, potentially adding on a stiffer spring or things along those lines? The answer is no. I think these were quite hard experiments in terms of, we had a lot of failures where, like, not a lot, but we would have failures of the spring coming, or the screw coming out and along these lines. So we were quite happy to get the animals for what we have for these. They're great questions. It'd be really nice to do. There's a lot of things to look at along those lines of looking parametrically, how is this controlled? I think a really interesting question, is, I think our experiments show the nervous system cares about these variables. We haven't really gone, like the question you're asking is getting at kind of, how closely does it care about it, right? Does it need to have zero, that medial lateral force? Or is it just kind of like, it's good enough. I have a little bit of discomfort or there's some load there, but I know it's not going to cause, massive dislocation. So as long as I'm somewhere in this kind of operating range where things are okay, I don't need to change anything, right? And there might be just kind of some kind of lazy control, that's kind of satisfying. And then if you hit some extreme, then you kick in and have to do an adaptation. So we haven't explored that entirely. I think there's a really interesting set of questions, and it intersects with the questions of the afferent, what sensory information is used as well. One idea, we're talking about joint afferents, there's lots of different joint afferents. There's ones that would be involved in looking at kind of strains within kind of the joint capsule, others that might be kind of giving us compressive load, but then there's other ones that might be telling us about inflammation or even pain, right? And those are all interact in different ways in the context of control, right? So you can think about if this adaptation could be driven by pain in some ways, right? And so it could be that there's a range of aberrant, medial lateral loads that don't cause pain, but you get to large enough and then you kick that in, and then that's when you get the adaptation process as well. So there's a lot of interesting kind of space there to be looking into. So anyway, but it opens up a lot of questions that we have not answered. I think there was a question back there. Yeah.
So for the rubber band experiment, did the insertion of the screws or like the rubber band itself like injure the rat at all, and would that have an impact on like how the experiment may go, or did they just accept the screws in their bones? Yeah.
So it's an important question. I mean, I think we did not look at so much. We didn't look systematically at, we did one surgery, we put in the EMG electrodes and we put in the screws at the same time. So we did not have EMGs before the screws and then after the screws to compare. Just superficially, the animals looked like they recovered really quickly and walked normally. There wasn't much of an effect there. We designed our experiments, though, to isolate the effect of the spring per se, right? So the idea is we were concerned about those issues about like, yeah, we put a screw into your patella, you're going to walk a little bit different. And how do you interpret that, right? So the idea is we put the screws in, allow the animals to adapt for at least 2 weeks to having the screws in the EMG electrodes, so that it kind of establishes a baseline. So whatever adaptation happens has occurred. Then we put in a delta adaptation by attaching the spring and look at the change of activation after attaching the spring. So even if the animal is doing something different because the screws were there, we can kind of recognize what the effect of that spring attachment was, right? And then moreover, we have the spring detachment as well. So that, I think it's kind of goes to, similar to like these, force field adaptation experiments or prism adaptation. You put on prisms and you adapt to the world being shifted, and then you take them off and you de-adapt. And we kind of have similar control, which I think is, that was a problem with the VL paralysis, right? Because we're cutting the nerve to VL. We don't have a de-adaptation process to look at of, reattaching the VL nerve and looking at going back to what it was before. So like that's, that experiment is open to the critique of saying, yeah, you're cutting the nerve. That's causing some weird change of activations. Maybe some of the EMGs adaptations you're seeing don't reflect control of these variables, but some kind of more undifferentiated adaptation or inflammatory response or something like that, right? So that's why I think the spring experiment helps to control for some of those issues along this line.
Thank you.
Cool. Yeah.
That's great. So I just have a question. If you have say functional neural stimulator muscle stimulator,
Yeah.
what's the best strategy to restore performance after let's say they are injured?
So the question is, if you could go in and control artificially the muscles, and so you could be kind of the artificial nervous system, and you now have a patient, which is your patient rat who has a VL paralysis, what would be the best way to activate the muscles to restore the function? I mean, it's an interesting question. I guess the two questions I back to is, are you asking what would be the best control strategy in terms of allowing the animal to behave the best? Or what would be the best rehabilitation strategy in order to get to the animal to the best performance?
In the box.
Both.
Would be
Yeah.
interesting.
I should have just said that you can only done the easy question. So is it or
There are actually two questions that just came in from outside.
Oh, okay.
So maybe we'll take one of those. Are you finished with that one?
no, I think I wish I were, but no, I mean, they're really interesting questions. So, I mean, I would kind of, from a bio-inspired point of view, what I would kind of say is that what we see the animals doing is what we should do in terms of control, right? Is kind of find this activation. We should increase rectus femurs, but maintain activation of VM, and that's a happy compromise. That's under the assumption that the nervous system knows what it's doing after these injuries, right? But we have not done, it would be where the computational biomechanics would come in, and that's if we're having the model, is like start from first principles, right? So if we were to say, here's the limb, and here are the muscles, and we get rid of VL, and we have some sort of cost function which has task performance and has these internal stresses and strains, what's the best strategy? My hope would be that we would kind of to the error bounds of my modeling, that we would have something that would look like what the animals do, but maybe that's not the case, and that would give us further insights. So I don't, those would be the open questions. Your second question, or my second interpretation of your question, in terms of rehabilitation is really interesting, and I don't have a good answer for that. I mean, how this would, that's the analysis we did in the adaptation was kind of looking at pre and then long-term post. Those transient periods in between, in terms of the animal doing, it has aberrant kinematics and aberrant EMGs. What's the error signal there? And what is it using to learn that it has these incorrect joint forces and incorrect task performance? And then how does that drive the adaptation we see? That's obviously really interesting questions. And then, the idea is if we understood that, then we could then think about doing things like error enhancement or ways to kind of promote sensory information to drive that rehabilitation even further. But that's, or perhaps activating locus coeruleus to kind of increase that adaptation process or to speed it up along these lines.
So in the interest of time, I think I'll let you take these two offline. You
Oh,
both
sure.
answered, and I think that was a really nice question to finish on. So
Okay.
let's thank our speaker one more time.
Not here.
Oh, yeah. We
Okay.
yes.
All right.